In section 2.7, we will look at what are called inverse functions. We have an f and a g, and it says, picking up from section 2.6, it says find the composite function. So it says find f of g of x. For f of g of x, we're going to take all of g and place it into the x of f. So let's try that. We equal 2. We're replacing this x there with all of this, x plus 2 over 3, and then that minus 3 is still there. That x became all of that. And now we're going to distribute, so this 2 is going to go into this x, and it's going to go into that 2. So we're going to get 2x plus 4 all over 3. And then we're going to get, we want this 3 to also be over 3, so we're going to write it as minus 9 over 3. So they have the same denominator. And then we're going to get 2x plus 4 minus 9 all over 3. And that will simplify to 2x. 4 take away 9 would be minus 5 all over 3. And that would be the answer here, 2x minus 5 all over 3. Okay, now the second part says, let's take all of g, place it into x. So take all of f and place it in x for equation g. So that's going to look like this. G of f of x, we're taking 2x plus 2x minus 3, and we're placing it into that x. I'll put parentheses on just so you can kind of see how they're connected. Then we have plus 2, and then we have divide by 3. Well, the only thing we have to do here is remove those parentheses after we can make the connection that it was x. So it represents the entire f function being placed into x, and we get 2x minus 3 plus 2 over 3. And this is going to be 2x minus 1 over 3. And that's all we would need to write for that one. 2x minus 1 all on top of 3. Okay, now it asks, are they inverses of each other? They're only inverses of each other if, so f, let's write this with a different color to accentuate it. F and g are inverses of one another if f of g of x equals g of f of x, and they both reduce to just x. So, and we'll see one where this happens, so you'll understand in a problem what it actually looks like. Our answers to a and b should have just been x. So it should have simplified to x, and they should have both been x. But since they're not, I have some equation. These are not inverses of each other. So f and g are not inverses. They weren't equal, and they didn't equal x. Okay, so let's look at another one and see if we can get two that will work. So problem 2, they want us to do the same sort of things. They want us to plug g into f, so we take all of this g stuff and plug it into the f function. So that would be f of g of x. So the only thing that changes, we have 7, we have 7. We have minus 2, division, division. The only thing that changes is all of this stuff's going to replace that x, so we get 7 over x plus 2. And we can see that these 2's are going to cancel, so this is 7 over x. And I had shown this in a previous video. If you have a triple fraction, the x will pop, whatever's on the very bottom will pop up onto the top. So we have 7x over 7, and those two 7's will cancel, and the whole thing simplifies to just x. Okay, now we got to go the other way. Now it says f and plug it into the x for g. So this one would be g of f of x. And so we have g is 7 over something plus 2. And that something now is all of this. So we replaced that x right there with all of that stuff, 7 over x minus 2. And now I'm going to use that same trick we just used. Triple fraction, this entire thing is going to pop up here. And so we get 7 times x minus 2 over 7 plus 2. Now don't distribute, so that 7 and that 7 will cancel. And we're just left with x minus 2 and then plus 2. The 2's will cancel, and we just have x. So this is an example where it worked. The two composite functions are the same. They both reduce to x, so they are inverses of one another. Oops, I clicked the wrong one. They are inverses of each other. And that's how it would work. So you would get it to reduce to just x. Okay, in problem 3, they tell us that f of x is 1 to 1, and I'll explain that with a drawing here later, is 1 to 1, and the function is 3x plus 2. So it's a very simple function. It's going to look like it's a straight line, and it's going to touch the y-axis at 2, and it's going to have a slope of 3. So this thing is going to cross like this, and it has a slope of 3. So a very simple curve. It is 1 to 1. 1 to 1 means I can draw, well, let me say that. We have problems designed just to teach you that. So let's wait on that. Okay, so part A says find the inverse. And I explained before, this is not a power. It stands for the word inverse. So here are the steps for this. Step 1 is replace f of x with y. Step 2 is swap x and y. Step 3 is solve for y, because we just swapped it, so now it's in a different spot, so now we have to solve for it. And then step 4 is replace y with f inverse of x. Okay, so let's try all these steps out on this problem, 3x plus 2. So step 1 says replace that f of x right here with y. So we're going to write it as y equals 3x plus 2. Step 2 says swap x and y. So where I had a y before, I'm going to write x. Where I had an x before, I'm going to write y. Okay, simple enough. Step 3, this is usually the hard part, is to solve for this y. So we have to now isolate this y, get it all by itself. So let's subtract 2 from both sides, so we're going to get x minus 2 equals 3y. The 2 on the right is now on the left, it became minus. And then we just have to divide everything by 3, so we get x minus 2 over 3 equals y. And then step 4 is to rewrite y, and I'm going to write it on the left side, not the right side, as f inverse of x. So the f inverse of x is x minus 2 over 3. Okay, so where do they want us to record that answer? Oh, so we have to find the domain. So let's look at the original function. So the original function, f of x, has a domain of all real numbers. It has a range of all real numbers. So the x values are going to hit minus infinity to infinity. And then the range values are it's going to go up to infinity, and it's also going to go down to minus infinity. So in the y, it's going to hit all positive and negative values, and in the x, it's going to hit all positive and negative values. Now, in the f inverse, its domain and range are just the come from the original problem. So the domain of the inverse is going to be the range of the original problem, and the range of the inverse is going to be the domain of the original problem. But both of these are minus infinity to infinity. So our F inverse equation works for all x. When they say for all x, they're basically saying minus infinity to infinity. And we just have to record our equation. It was x minus 2 over 3. And now it says verify that the equation is correct. So they want us to plug in the inverse function into the original function. So we're going to put x minus 2 over 3. All of that is going to go into the x of the original problem. So the original problem was 3 times x. But instead of x, we're going to write x minus 2 over 3. And then they had a plus 2, so we're going to say plus 2. Now these 3's are going to cancel, so you just get x minus 2 on top, and then plus 2, and those 2's will cancel, and you're left with x. So that equals x. In this one, they want us to take the original function, 3x plus 2, and plug all of that into the x for our inverse equation. So our inverse equation says take x minus 2, but instead of x, we're going to write 3x plus 2. So basically, let me give it a little color here. I put 3x plus 2 in place of this x right here. Then we still have minus 2, and we still have division, and we still have the 3. These 2's are going to cancel, so I have 3x divided by 3. The 3's will cancel. We're left with just x. So if we get this, we plug our inverse into the original function, we plug the original function into the inverse, and we get x's, then the equation is verified. It is verified that it works as the inverse. A lot of steps there, but we'll do a few of these, so hopefully it'll catch on. Okay, 4 is the same thing. They gave us the function the 18th root of x, kind of an interesting problem here. It's actually, no, it's not too different from the square root of x. So the 18th root of x is just like the square root of x. It starts at 0 and then it flattens out really fast. But it's, let's actually do the domain on this because we're going to need it. The domain starts at 0 and includes it, and it goes off to positive infinity. So this would be f of x. Let's do the range while we're at it too. The range would also start at 0 and go off to infinity. So this thing has an angle on it, so it's going to go up to infinity as well as it goes to the right to infinity. Okay, so now we can do our steps. So step 1 says write f of x as y. So y equals the 18th root of x. Step 2 says swap x and y. So where it was y, now I write x. And where it was x, now I write y. Step 3 says solve for this new y. So this new y is buried under this 18th root. So to solve for it, we are going to take, so what gets rid of a square root? What gets rid of a square root is when I square something. To get rid of the 18th root, I have to take this to the 18th power. But if I take that side to the 18th power, I'm going to take this side to the 18th power. So we're going to get x to the 18th, and this 18th root and 18th power will cancel, and I think I wrote something wrong here. It's not an x anymore, it's a y. This is the 18th root of y, and those 18s will cancel, and you're left with just y. And then step 4, I'm going to write y on the left side, and I'm not going to write it as y. I'm going to, let me write here. So this is the same as y equals x to the 18th. Just swapping sides. Step 4 says replace y with f inverse, and that's going to equal x to the 18th. Okay, so x to the 18th is interesting. It's going to look like a parabola. It starts at 0, and it's going to go up like this. Okay, and we can see that inverse function, its domain and range are going to be borrowed from here as well. This range is going to become the domain of this one, and this domain is going to become the range of this one, but they're both 0 to infinity. And you can see it in the picture. And so that is this one right here. So x is positive or equal to 0. So we're going to record x to the 18th as our inverse function in slot B, because that's the domain, is 0 to infinity. Okay, now we verify. So they want us to plug in the inverse into the original function. So if I take the inverse x to the 18th and place it in the original function, which is the 18th root of x, I just replace that x in there with x to the 18th. This 18th root and this 18th power will cancel, and you're just left with x. This one says take the 18th root of x, the original problem, and place it into our inverse answer. So we're going to have the 18th root of x placed into this function, which just says take whatever you have and raise it to the 18th power. Well, again, 18th root and 18th power will cancel, and this will equal x. So they both equal x, so it is again verified. We verify that that has to be the inverse, because when we plug it in, we get x to come out. In fact, the line y equals x is a 45-degree angle line that goes like this. And that is going to give us a visual clue that we'll see in some future problems. So if I drew this correctly, you'll see there's some symmetry there. That's not a coincidence. And we'll see that here more in the graphing problems. Okay, so now we're going to introduce this idea of one-to-one. So before it said these functions are one-to-one. It said that. And then therefore we could calculate an inverse. So if a function is 1 to 1, it can have an inverse. And the way we test to see if a function is 1 to 1 is with the horizontal line test. So use horizontal line test to see if the function is 1 to 1. And the horizontal line test is very simple. It's the same as the vertical line test, except for instead of vertical lines, we're drawing horizontal lines. And we're just looking to make sure it hits the graph at most 1 point. So a function passes the horizontal line test if any horizontal line hits the graph at 1 hits the graph at most 1 time. Okay, so we just do this by running horizontal lines. So horizontal line missed the graph. That's fine. It's still good. It could pass the horizontal line. Horizontal line doesn't hit it. Still good. Horizontal line that hits at 1 point, it's still 1 to 1. It's okay. But then anywhere down here, I hit twice. This is going to fail horizontal line test. If it fails horizontal line test, it is not 1 to 1. If it's not 1 to 1, then there's no inverse. So a lot going on there. But it's a simple test to run. So does it have an inverse? No, because it failed the horizontal line test. Okay, so even though my camera view is covering up a bit, if we do 6 right away, I can just draw one line right there. It hit 3 spots, and it doesn't matter how many times. If it hits more than once, 2 times, 3 times, however many, that's going to fail the horizontal line test. Therefore, it's not one-to-one. And therefore, there is no inverse. So this one would also be a no. Does the graph represent function has an inverse function? No. So hopefully those are pretty simple. Just horizontal line, hit more than once, you're done. No inverse. Okay, in 7, we can start, if we want, with the horizontal line test. So horizontal line, all these horizontal lines are hitting at only 1 point, 1 point, and 1 point only. So this one's going to pass the horizontal line test. So therefore, it is 1-to-1. And therefore, it has an inverse. Okay? But this wants us to actually draw that inverse function. So let's see how we would do that. To do this, we are going to just need the ordered pairs for these dots. So we have an f function, we have an f inverse function. And you'll catch on to this pretty quick. Record these dots. This first dot is 0 in the x minus 2 in the y. So 0 in the x minus 2 in the y. This dot is 1 in the x and 0 in the y. This dot is 2 in the x, 2 in the y. So if my ordered pairs here are x and y, then the ordered pairs in my inverse are y, x. So you just flip them. So the inverse function, if the original function had a point 0, minus 2, the inverse function has a point minus 2, comma 0. If the original function had a point at 1, comma 0, the inverse has a point at 0, comma 1. And then they both share 2, 2. When you swap those 2's, they don't really change. So these are the 3 dots that are going to be associated with the inverse function. So let's do a different color. Let's say green. So I just have to plot these points. Minus 2, 0 would be here. 0, comma 1 would be here. And 2, comma 2 is the shared dot they have right there. And if I connect these dots, get a straight line that looks something like that. And so you would have to plot in your homework, you just have to click these 3 dots, type in the ordered pairs, or click on the actual graph, and it'll fill in the line, and that's it. But this is where I wanted to show you again that line y equals x. So there's a line y equals x that looks like this. And what we find out is, so we found out that when we plug in f of g of x, and if it's equal to g of f of x, and it's equal to x, then f and g are inverses. Inverses of each other. And on the graph, the way it shows up is they're symmetric about the line y equals x. So if you look, this section and this section are symmetric. So symmetric about the line y equal x. And hopefully you can see it. You can kind of see on my drawing here how if I were to flip this this top portion across that line, y equal x, they'll fit perfectly on top of each other. And also notice that any point that touches the y equals x line will be a shared point between the 2 curves. Okay, so graphically, hopefully these are kind of simple creatures to manage. Okay, so 8's the same kind of method here. Let's see if color can help. We have f, and the points they give us are 0, comma 2. And there's a point at 1, 2, comma 1, looks like. 2, comma 1. And then in, I guess, black they use for the inverse. These would flip, so 2, comma 0 and 1, comma 2. So this one's a little tricky because it overlaps kind of, it's kind of small. So 2, comma 0 is right here, and 1, comma 2 is right here. And they're going to be symmetric about this line. So it's going to look like, this drawing is hard to get correct. It's going to come in through this dot, that dot, and then go like that. It's going to look something like that, if you can imagine the symmetry. And so our best picture is got to be B. So dots are kind of close to each other, I realize, but hopefully you can look at it and see that B is the only one that would work. Okay, for 9, we're going to actually use some of what we learned for graphing transformations. So we have a function in, what colors do we want to use for this? Black, it looks like they use for the original function. And this is going to be a parabola that's shifted 4 to the right. So our original function here, 4, it's a parabola, so it's going to look like it's going to go up, and it's going to go up on this side. But this is what's interesting about it. It says for x less than or equal to 4. So to make this 1-to-1, they say, let's chop off this, anything bigger than 4. So to make it 1-to-1, so we can pass a horizontal line test, we just have that chunk. Okay, this is f. Okay, but now they want us to find the inverse. So this is where we've got to run our steps. So step 1 is replace f of x with y. Step 2 is swap x and y, so it's now x equals y minus 4 squared. Step 3 is solve for this y. So to solve for that y, we have to unbury it from the square. To get rid of that square, we're going to square root. But if you're writing a square root, you have to also add plus or minus. On the left, we'll have x plus or minus the square root of x. And on the right, we'll have y minus 4. So that square root and that square will cancel. Now the last step is to add 4 to both sides. So we'll get 4 plus or minus root x equals y. And let me rewrite that as just swap these, y equals 4 plus or minus the square root of x. And then step 4 is to say, replace y with f inverse. Okay, square root of x is a function, we just saw this actually. This would be two functions. It would be, here's square root of x, here's minus square, let me use color. Here's minus square root of x. This 4 out front is just going to shift both of these curves up to 4. So we would have the possibility of it being like this and like this. Okay, so that would be 4 plus or minus root x. Now let's see how that's going to look on our drawing over here. They're going to both start at 4, but do I take plus root x or do I take minus root x? And it turns out, if I put in my line of symmetry, which should be a 45-degree angle right through these, 45-degree angle right through the origin, that this top portion will not work. So this portion is not symmetric, so we're going to erase him. So the answer was the minus root x portion. So this is for minus root x. So that is going to be our inverse function. And we can already see the answer. Our drawing matches pretty closely to B. Okay, now that we have the picture, they're going to ask us about domain and range. So let's go down to that. We know our answer is B, so we can actually use the drawing now to answer this part. So let me use color here to help us. The black curve right here, its domain goes from minus infinity to 4. So the domain of f of x is minus infinity up to 4 and including 4. The range of f of x is, it starts at 0, including it, and then it's going to go up to positive infinity. Okay, now the beauty of this is that just gave us the answer for the other two blanks, because this answer is going to go here, and this answer is going to go here. So the domain of the inverse is the range of the original one, and the range of the inverse is the domain of the original function. And you can see it in the graph. So the red curve, its domain, it starts at 0, and then it's going to go off to positive infinity to the right. And its range, the highest it ever gets is positive 4, and it's going to go down eventually to minus infinity. So that's how that would match up. And graphically, hopefully, it's pretty easy to see. Okay, problem 9 is very similar. We're going to have a cubic function that has been shifted 9 to the left. So let me draw this a little differently. 9 to the left. So over here at minus 9, we are going to have this function that looks like a kind of a sideways S or something. Okay, so that's f, and then we'll see what happens with f inverse. So let's solve for f inverse. And I'm using red for that. So step 1, replace f of x with y. Step 2 is swap x and y, so x equals y plus 9 to the third. Step 3 is solve for this y. So we have to unbury that y. To undo a third power, we're going to take a third root. But if I take a third root of the right, I have to take a third root of the left. Now, we don't add plus or minuses when this root is odd. So I did in the last problem because the root was even, it was 1/2. This is 1/3 or 3, which is odd, so I don't need a plus or minus here. So we're left with the cube root of x, and it's equal to this 3 and that 3 cancel, y plus 9. Now we just have to subtract 9 from both sides, and we're going to get the cube root of x minus 9 equals y, and then I'm just going to write it on the left side instead of the right side, the cube root of x minus 9. And then step 4 says that is the inverse function, cube root of x minus 9. Now cube root of x, the parent function, looks like the s but turned on its side. So it's going to come in here like this and then go like that. The minus 9 portion is just going to shift this down 9. So it's going to come in here, go through minus 9 and through. So in our drawing over here, minus 9 would be about here. This thing is going to go like this and then over. And if I've drawn it correctly, it should be roughly symmetric about that line, y equals x. And look at it, a little crook-eyed maybe. It does look like it's going to be symmetric. And it also gives us the answer to the correct drawing. The correct drawing is A. But let's record what the inverse was. It was the cube root of x minus 9. Okay, now that we have the right picture, let's go down and calculate the domain and range. So the domain, so the answer was A. And looking at the black curve, the original function, its domain, so it's going to go left to minus infinity, and it's going to be angled up to the right to positive infinity, so it's going to see everything. Its range, it's going to go down to minus infinity, and it's going to go up to positive infinity, because those lines are angled, so it's not only going up, it's also going to the right. But the range is going to be everything also. Well, that makes our next set of answers easy. This answer goes here. This answer goes here. So they're both all real numbers for the domain and range. And you can see it in the picture. This red line is also going to go left and down, and it's going to go right and up, both to infinities, and minus infinity and minus infinity. So it's going to see everything. Okay, 11 and 12 aren't too bad at all. It says, let x equal 7 and go to the G table. So go to the G table and let x equal 7. So here's the G table, and go to x equals 7 and record the number. So the number is minus 5. So now I have f, g of 7 all became minus 5. So now this says let x equal minus 5 and go to the f table. So I go to the f table, and I go to x equal minus 5, and I record the answer. This is equal to 7. So we would record 7. Okay, this is saying almost the same thing. This is saying g of f of minus 2. So it says let x equal minus 2 and go to the f table. So we go to the f table, and we go to x equals minus 2, and we record the number. That is equal to 2. So now, f of minus 2 became positive 2, so now we're looking for g of 2. Well, this says, let x equal 2 and go to the g table. So we go to the g table, where x is 2, and we record the answer, minus 4. And that would complete section 2.7, and that is all we're going to cover from chapter 2.